Okay. So I got a question from homework 39 and 3.6. Oh, okay. Question?
3.6?
Yeah. Now the instructions say use logarithmic differentiation. Personally, I would never actually do that, but it says to do it on this problem, so you do it. Normally, you would use logarithmic differentiation when you have a problem like this, where a function of x is stuck in the exponent and it's on in a function of x. It's like, holy shit. No rule directly works on that, so you have to break it apart somehow. This one, why would somebody possibly use, what does it mean, logarithmic differentiation?
Implicitly differentiate.
ln both sides.
ln both sides, and then do what you said. I like it. So if I ln both sides, what good does that do me?
You can bring the two.
Well, what can you do first?
Break it up.
Out of both terms.
Good. Well, and with the one in between?
Plus.
So I haven't taken any derivatives yet, right?
Nope.
Thanks. And now you can do what?
2 down.
Take a 2 down, just so I don't have to rewrite the whole damn thing. Is that okay? Can you guys handle? It's not too bad. Now, invariably I always get somebody tell me, well, why didn't you just teach that the natural log of something's derivative is just the derivative of that over itself? I'm like, I did. That's a shortcut. How do you take the derivative of ln of something? It's 1 over that something times the derivative of that something. That's chain rule. This makes it feel like it's a different kind of rule. That's why I don't like teaching this. This is a nice little shortcut. That's what it's always going to become. But this reinforces that it's chain rule that's making that happen, right? So yes, great. That's awesome. But that's really what's going on. So when I take the derivative of ln of y, so now I'm going to do d by dx to both sides.
1 over y.
Yeah, 1 over y, dy dx. Or y prime, really, if you want to, because they only got y and x in here. Equals 2 over
X squared.
x squared plus 2 times,
2x.
yeah, x squared plus 2 prime. Let me just write the rule out a little bit. So the derivative of the natural log of something is 1 over the thing inside. And then the thing inside gets a term. So I still have people that are, I'm not even sure how to, there's so many different ways to make mistakes. There's no single way for me to, but I get people that do stuff like, this derivative would be 1 over sine, and what's wrong with that? Do you guys see what's wrong with that? What's the derivative of natural log of something? 1 over that thing times, right? That's just one little thing that happens, and then there's a lot of other stuff. Plus, same thing over here, right?
4 over whatever. 4x.
Right. I like it. So still a few of you guys that seem to believe that it's a guessing game. I'm not getting through somehow, but I got to keep trying. But a lot of you guys are doing fine, but some of you guys, you don't guess at how many derivatives. You do the immediate derivative that's in front of you. So the derivative of ln of anything is 1 over that thing. There's a 2 there, so I put a 2 there. And then the inside gets a turn. So I'm not going to worry about that until the next step. Unless you're more comfortable with it, you can just do it all in one step. So then I get 1 over y dy dx equals, derivative this is times 2 plus derivative this is times 4. And then I'm going to multiply, to get dy dx by itself, I'm going to multiply by y. And what was y? That mess. So I'm going to multiply by y. So next to this, I'm going to put that. right? Because they're going to multiply y up, and y is that. So personally, to be honest, if it didn't say use logarithmic differentiation, I hope to God nobody would. Because what it ends up at is nothing pretty. And actually just doing this derivative directly, would it be really all that hard? It would be primarily what? Product rule, and then there would be some power rule and chain rule in there. Not a big deal. It's this kind of thing, like I said earlier. This is essentially impossible unless you do logarithmic differentiation. However you say it. So yeah, well, yeah, of course I'm going to use it here, because otherwise it's impossible. Okay.
Would you want us to still try to simplify that down, or just multiply it all by y?
Yeah, I mean, you could put this on top of both and have like one of these cancel, right? But I mean, does that really get you anywhere better?
No, that's what I was asking. Like,
So no, I would actually expect you to write that in here.
Oh yeah.
But you know, I get a little board license not to add. Sorry. How are we doing? Are we okay? Alright, I'm just really worried about a few of you guys. I don't want to get to the point where it's going to be too late to be able to do a damn thing about some of the mistakes I'm seeing. You've got to come see me if you're making these major mistakes. Again, if you make me say, what? on your quiz or homework or something, that's a cry for help. I'm like, please come see me. Please let me help you. Please, dear God. Alright, it's up to you. If you don't want to, it's up to you. Okay. Anything else from homework stuff or quiz? Yeah.
27 on 36.
Ooh, yeah. So 3627. So it just says differentiate this and find the domain of this. Well, like that. So if I was going to differentiate this, what procedure would I use? Quotient, all day long. So f prime. Top first, the derivative of the top times the bottom. So this is 1 times this, minus the top times the derivative of the bottom. Right? That's the rule. All over bottom squared. I like it. So now the only piece of this I got to do is this, and then see if there's any other terms, right? So how the hell do I do that? Derivative of 1 is 0. Then I got a negative. Derivative of ln of x minus 1 is, and times the root of the inside, but the inside slope is just 1. So that's, so anything, if the inside is a slope of 1 linear thing, you don't have to worry about chain rule. It's just going to be a 1. I don't know if you guys get me on that. All over. Now this, of course, this is exactly the setup where I'm going to have somebody make me cry and cancel one of these out. Right? Actual tears. Right, so if you get your homework back a little plot, I'm sorry. Not really. But because it's a minus, I can't divide into a minus. Division's not that powerful. So I just have to simplify the top. And the only thing I really do to the top is multiply these out, right? What do you get over there? Plus x over x minus 1. And then, technically, we don't like fractions inside of fractions, but, so you could multiply top and bottom by x minus 1. But it doesn't make it any better, to be honest.
So we can just leave it like that?
You can leave it like that, that's fine. Yes, ma'am.
You see? You see?
Derivative of 1 was 0, and then there's a negative sign?
Oh.
Yeah. Cool, how's that?
How do you find domain?
Oh, so domain of anything that looks like that, what can't happen? That's the way you start. When I say find the domain of this function, you say to yourself in English, what can't happen? In something that looks like this, what can't happen? Bottom can't be zero. I mean, see, that's crazy. Any domain works like that. You say in English what's got to happen or what can't happen, and then write it in Mathesh. And then solve. Almost too good to believe. Now you got to worry about how the hell to solve this.
Set x, yeah, solve for x.
Yes.
Okay.
Can you be more specific?
You can move
Yes.
elements. Would you say greater than 0? I mean,
No. If it was inside of a square root, then I would.
Yeah.
But like a fractional thing, the bottom cannot equal 0. So it's no greater than here.
So you can move elements.
Yeah, I can move that over. So 1 equals ln of x minus 1. And then I can, so I get x minus 1 equals e. So x equals, or not equal to. Right? Not equal to. E plus 1. So x can be anything except e plus 1.
On the bottom.
Now, that's the bottom. That's one thing. Now, is there another part of this that has a restriction in it? The bottom can't be 0, so I know x can't be this. What else can't happen inside this function?
The inner function of ln can be less than 0.
Good. So the inside of the ln, so now it's coming back to what you're saying, right? So we got this is true because that's on the bottom. This can't happen because that would make the bottom 0. But also, and, where'd it go? X minus 1 has to be
Greater than 0.
greater than 0 because it's inside of an ln, right? Domain, when they say find the domain, they're inherently telling me they want real numbers. So ln, for ln to be real, the inside's got to be greater than 0. And what makes this greater than 0? X greater than 1. So x has got to be bigger than 1, and also x cannot be e plus 1. And what's e plus 1 around?
3 points.
3 point, yeah, exactly.
Relate to it.
So if I wanted to write this in interval notation, it'd be 1 up to e plus 1, and then e plus 1 up to infinity. Right? It's from 1 to infinity, skip e plus 1. That's what that says.
It looks funny.
I know. It does. E plus 1. Okay, anything else? Okay. There was something else on here I wanted to talk about. So we already talked about looking for where you can simplify first, right? That was a big problem with this quiz. I didn't take points off if you didn't simplify first. A lot of you guys didn't simplify first, but got the right answer eventually, after a lot of shit. So now you know you need to look to see if you can simplify things. And look, if there's an ln in the damn thing, then you go, The place you got to be careful about is what powers can come down on an ln. So one of these can be simplified, and the other one can't. The bottom can, and the bottom can't. Right? But what did I say? Did I say the bottom can and the bottom can't? Oh, shit. What is it? Thanks, man. So this, the bottom can and the top can't. So what? How can you rewrite this? 2 ln x, and then this is what's that? So how would you take this guy's derivative?
7.
Yeah, this guy would be easy. So y prime is something to the 7, so it'd be 7, that thing to the 6 times the derivative of the inside. Right? Yeah, so it'd be 7 over x ln x to the 6 like. Right, that would be 1 over x, so I just pull it out there. Cool. You guys with me? So everybody's part C on the quiz, number 1, was one you could not simplify first. And everybody's part B was one that you could simplify first. And of course everybody's 1A was, you can simplify that first also. So A and B were simplifiable, and C was not. Okay, alright. So getting back into where we left off. We had just gotten a little bit into related rates. Yeah, there you are. So the problem we did is a classic problem dealing with Pythagorean theorem. Let's do one that doesn't deal with that. Here we go. Beautiful. I love it. Example 1. So in example 1, you have this spherical balloon, and they're going to pump air into this balloon at a certain rate. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. What symbols do I give that?
Volume percentage?
Talking about air?
Cubic centimeters is
Volume.
volume. So it's the change in volume over the
That's
change in time. So it's a rate of change of volume. Right? So it says air is being pumped in so that its volume increases at a rate of 100 cubic centimeters per second. Is that cool? So, a huge deal with these problems is being able to identify the numbers they give you with the appropriate symbols. If you can't do that, you're screwed from the beginning. Because you're going to have this equation you're going to set up, you're going to take derivatives, and then you got to know where the hell to plug stuff in. Right? So you have to identify the numbers they give you with the symbols. Right? So this is change in volume over change in time. That's what this is. And you can just see from the units, you can see. You don't even have to read the damn thing. Just, you look at the units. Bless you.
Is that an S or a 5?
Let's try to be an S. Is that better? Let's see what the verse says. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? I love it. How fast is radius increasing when diameter is 50 centimeters? Now, what's the immediate? Can somebody see the immediate concern? They're asking me about what?
The radius.
Radius. And they're telling me something about the
Diameter.
All right, those silly, stupid people. So what's the... At the time when the diameter is 50, the radius, of course, is also 25. That's going to be more useful to me because everything they want is about the radius, right? So look for that kind of thing. So the whole point of related rates is, can you set up an equation that represents the volume, in this case, at any time, and then take the derivative to see how quickly it's changing. So if you can set up a relationship between volume and, in this case, radius, then you can take the derivative and you'll have a related rates equation, the relationship between the rate of change of volume and the rate of change of radius. So it's almost too beautiful to believe. Any equation you've ever seen in your whole life, the perimeter equation, right, is for a rectangle, it's 2L plus 2W. So then dP dt would be 2dL dt plus 2dW dt. So that's the relationship between how quickly the perimeter is changing and how quickly the side lengths are changing. Do you guys understand? Any equation you can set up that relates given parameters of a problem, given dimensions or whatever, when you take a derivative, that's automatically a relationship between the rate of change of those things. That kicks so much ass. Unfortunately, a lot of these problems have, I don't want to say it like that because I love it, but these problems have situations where setting up the equation in the first place is interesting. Right? But the minute you get it set up, you just attack it with derivatives and then plug stuff in the right place. It's all about getting the equation set up. So what equation am I going to use here? This is not one I got to set up. This is just a known equation. Anybody know what the volume of a sphere is in terms of radius?
The
radius
what's that, 4/3
4
power?
over 3
Good. 4/3.
Yeah, cube.
I could use a big R, it doesn't matter.
The diameter is 1 over 6 dv squared.
Yeah, since the diameter is twice the radius, you could, or the radius is half the diameter, you could actually rewrite this in terms of diameter. But we don't have to because we were smart and we put everything in terms of radius to begin with. I love it. I like it. But you could, if you wanted to leave the diameter, you can put everything in terms of diameter. Cool.
Let's say we don't know that equation. Are we going to have like a chance to like find it? Like, let's say for the homework, we can just Google it.
Totally.
Yeah.
On a test, if there's something like that you forgot, you can come up and I'll make fun of you for a little while, and then I'll tell you. Normally when people come up and they ask me, they've written it down correctly, they're just not sure about it. So I tell them, yeah, that's right. Part of me just says, you should know this. You really, really,
I
really
don't
should.
know.
I
see it now.
I understand. So now I've got the relationship between volume and radius written, but I need a relationship between the rates of change of those things, right? Because what is the question in symbols?
Find the radius.
In symbols,
dr,
dt. So that's what I'm trying to solve for, right? They tell me dv dt. I'm trying to solve for dr dt. So how do I take the derivative of this? I'll do this side.
4r squared.
Yeah, if you take the derivative of r cubed, it'll be 3 times this. So the 3's will cancel. Is that cool?
Yeah.
4 pi r squared. Sounds good so far. So far it's great.
dr.
I like it.
Pi's just a number.
Pi is just a number, exactly.
So
Don't give me no d pi dt. That would be 0.
dv over 4br squared dt.
Yeah, exactly. I mean, now it just throws things in and solve for dr dt. Real quick, before I get too far, what would dv dr be? What's dv dr? Can you make sure you guys understand? Totally, but what is it? I like it. So that's what it represents. That's kick-ass. So if I change the radius by a certain amount, this would tell me how much the volume would react to that, how much it would change. So what is it? There's only one little difference between what we already did.
It's 4 pi squared?
Yeah, it's 4 pi r squared. Because what would it be? It would be dr what?
dr.
Which is 1. So why does that show up? Because I'm taking the derivative with respect to time now. I want rates of change over time. Do you guys understand? So that's why, what happened?
You asked me for dr.
But you're cool with this?
Yeah,
So why is that a dt?
because it's relative to time.
Because it's dt there, right? Because I'm taking the derivative with respect to time. So if I did it with respect to r, wouldn't this be dr? Same way that this was dr dt, right?
I believe you.
So, and this is actually kind of silly, but here the radius is a function of time, right? This balloon's radius is going to change over time if I'm pumping it with air, right? So I have to do chain rule because the inside function is a function of time. So chain rule has to happen. Is that cool? So over here, I wouldn't even do this because the inside function is a function of radius. If I'm taking it with respect to radius, I don't need to do it because it's going to be 1 anyway. You can see it happening. What's on the bottom when I'm doing this derivative? dr. So taking the derivative of the inside with respect to itself, it's 1. That's another way to think of it. It's like, how much are you going to change? How much older are you going to get versus how, in relationship to how much older you get? Well, I'm getting older at the same rate that I'm getting older. That's why it's always 1 when you do it with respect to itself.
Okay.
I don't know if that makes sense at all. That is kind of actually what's going on there technically.
How do you know when you just add a d on the top? It's like d by dx.
So, and we're not quite done with this yet, right? But it's sort of like saying, when do you just have a square root symbol sitting there? Because if I wanted to write the square root of x, I would do this, right? If I want to write the derivative of x with respect to x, I would do this. So I would put an x into the square root. I would put an x into the derivative. So the d by dx is exactly like a square root symbol. By itself, it doesn't mean much until you actually put something inside of it. So a square root symbol by itself does mean something. I know it's a square root, right? But what does this actually totally mean? Nothing. It's not even the square root of 0. It's the square root of empty space. So it doesn't mean anything really until I put something inside of it. So d by dx is a command. All right, what am I going to do that to? I don't know. They didn't tell me, right? So I have to put something inside of it, and then I can do it. Does that make sense? So d by dx is like the square root. It's like sine of, square root of, natural log of, d by dx of. And to be honest, if you're going to take like anybody got up to diffie differential equations, you'll be calling this thing an operator because that's really the next level of function. Really is an operator. But I won't say that again. That'll be later. All right, so let's finish this guy out. What can I put in there now? Yeah, I know this is 100. What's R? 25. And then dr dt, I don't know. So now I can solve for that. I just got to divide by that and whatever the hell that is.
625 multiplied by 4.
Yeah.
And then 100.
Thank you for that. That's good.
No, 104.
So 100 divided by 25 is 4. Divided by 25 again is 0.16. Divided by 4 is 0.04. Divided by pi is whatever the hell it is. 0.01 something. Did somebody do that yet?
0.127.
Sorry.
I had a calculator.
0.012 something. Look at Jeff. He knows math. 0.012 what? Thanks, Steve. What?
Centimeter.
Centimeters?
Cube.
No.
Second.
All you got to do is look at the symbol. Change in radius. Well, what's radius measured in? Centimeters for this problem, right? What's time measured in this problem? Second. Yes, sir.
How many numbers do you want after a decimal? Because usually it's like 3 or 4.
Yeah, when in doubt, do 2 non-zero. Does that make sense?
Okay.
Do you know what I mean? Don't do 0.01, do 0.012. When in doubt, do that. That's fine. That should be enough. Yeah. Ooh, yeah. Let's go to science. No, it's not good. You know, in math, we call it sig digs. So, instead of significant digits, instead of significant figures. Wait, it's a totally different thing, so let's not do it. All right.
Can I leave it like 1 over 25 b? Or should I like calculate it? How much to it?
Oh,
You divide it.
since this is a physical problem, we do want to go ahead and plug in an approximation for pi. You hit your pi button on your calculator. You do want to get it, because it's a physical problem. You wouldn't say, well, it was changing by about 0.07 pi. It's like, who are you? I live about pi squared miles away. No, you don't. Stop it. You see what I'm saying? So if it's a physical problem, we do want to go ahead and take it out to its non-exact form, its approximate form, because that makes more physical sense. I like it. Good question. Okay.
And I wanted to mention this formula is like similar to the
Surface area.
Yeah.
It's interesting, if you look at a sphere, let me see. This is kind of cool. If you think of it. The surface area of a circle, of a sphere is 4 pi r squared. So what's interesting is, if I increased, so look, let me see if I can go with this further. If I increase the radius by just a little tiny bit, it's like applying a layer of tape on there, right? I'm trying to make it thicker. Do you guys see what I'm saying? Mm-hmm. And then so I lay some tape on it. So this little bit would be dr. This is how much the radius changed, right? So how much would the volume change? Well, it's like I just added another surface on top of it. So how much would the volume change? By a surface amount. This is the surface area. So if I cover it with tape, the volume is a little bit bigger now. Is that cool? How much bigger? That surface area, 4 pi r squared. So that's why the derivative of the volume is the surface area, because that's how much the volume would change. If you didn't understand what I just said, you don't have to yet. But it is kind of neat to see that. Sort of like, what's the area of a circle?
P r squared.
Pi r squared. And what's the derivative of the area with respect to r?
2 pi r.
And this is also the
Circumference.
I like it. Because if I change the radius by a little bit, how much does the area change? It's like applying tape to around the circle. It's gonna change by 1 circumference amount. It's really kind of neat. Yeah. I love that shit. So if I extend the radius just a little bit in all directions, it's the same as like laying on some tape around there, right? The thickness of the tape represents the really small change.
Yeah.
So how much did the area actually change by? 1 surface, well, not surface in this case, 1 circumference worth. The area changed by this, a circumference amount. It's neat. If you don't quit that, that's enough of that, sorry. It's really kind of neat. I like that you pointed that out, but it was a little early for that. That's all right.
You got another layer, it's 1 layer.
Exactly. Yeah. Let's see. I do want to do one more type of problem, and then I'll let us out. This classic problem. Where are you? Give me one.
Is it the latter one?
No, that's too classic. It's just stupid. A cone problem. There's got to be a cone problem here somewhere. Or maybe I could just make one up, you guys. Yeah, let's make one up. All right. Holy crap and a half.
That's good, John.
Let's say that well, let's just go I'm not going to do like that. Let's say the radius of this is r. Actually, I'm sorry. I'm going to give us this real radius. Let's say the radius of this is 10 millimeters. And let's say the height of this is, what you got, Jeff? I don't know. 12 millimeters. I like it. Go with me for a second. And I'm going to fill this cone up. I'm going to start pouring some water into this cone, right? Some H2O. So there's a thing, a little hose coming in there. And holy crap. Some water's coming in. That look horrible. All right. That's water. So the water level is somewhere here, right? Is that cool? So let's say that I'm pouring it in at a rate of what you got, Jeff? 2 cubic millimeters per second.
And that's
You guys with me? So it feels like that last time with the sphere, but I'm just filling it with water. I want to show you this because it's weird. How at some arbitrary point, how tall is this? What's the height of the actual cone of water?
H.
Good. I don't know. It's h. And what's the radius of